Okay, good morning. So, yesterday I have given you one problem where the liquid subcooler was given, and you need to calculate the COP of the system with the liquid subcooler, where subcooling was done from 40 degrees Celsius to 5 degrees Celsius. So, let me give you the key parameters. In this case, m dot LP is, so I hope you all have done this problem, and if you have solved, you would have got the value of m dot LP as 0.02972. Please check, have you got the same value for m dot LP? Okay, closer. M dot dash is the actually flash mass in the flash chamber, so it is 0.0075427. Have you got this value? Sorry? Okay, you got the correct value then. Yeah. Then m dot HP, which would be m dot LP plus m dash, it comes out to be 0.037,263. And now work you can easily calculate, because that will be m dot LP into enthalpy differences. So if you calculated enthalpies correctly or not, you can verify. Your first low stage compressor work is 6.97 kilowatt, and high stage compressor work is how much? 7.39. Okay. And now if you calculate the COP of the system, I got it 2.45, 2.448. Okay. And what COP you got it? 2.33. Okay. So maybe values are actually closer. Now after this, so those who have not done this problem, they can actually refer to this one. And now let's talk about the next problem. So next problem we will try to take up of a multi-evaporator system, and in that multi-evaporator system we will try to fix even a few more components. So let me read the problem. A two-stage ammonia refrigeration system serves evaporator 1 at minus 40 degrees Celsius and evaporator 2 at minus 2 degree Celsius. So TE1 is at minus 40 and evaporator 2 is operating at minus 2 degree Celsius. Now both the evaporators are of 10 tons of refrigeration capacity. Okay, so I think there are 3 final year students also, so you can inform them as well. Okay, so both the evaporators are having capacity of 10 tons of refrigeration. Then and vapor leaves both the evaporators at saturated state. So in evaporator, transition happens from liquid to vapor. So whenever vapor is leaving, that is leaving at saturated vapor state from both the evaporators. Is this point clear? Now last minute reading will not work. You focus on numerical problem only. Okay, the condenser is operating at 40 degrees Celsius and subcooling heat exchanger subcools the liquid from 40 degrees Celsius to 5 degrees Celsius. So again, the same conditions are there. There is a liquid subcooler. Of course, flash chamber is within the flash chamber. The subcooling is happening, and liquid subcooling is being done from 40 degrees to 5 degrees. Is this not clear? Then same question. Now we need to define the mass flow rate, work requirements of both the compressors, heat rejection in the condenser and COP of the system. Okay, so can you tell me, if I have to draw this on pH diagram, how it will be looking like? This problem is identical to the one which I have given you for homework problem. The only difference will be I will be having one more additional evaporator. Okay, so pH diagram will be how? Three pressure conditions. PE1, PE2 and PC. Okay, I have 1 to 2 process. Okay, again one thing I missed. So it is also having a water intercooler. So same parameters are there, same conditions are there. So it is also having water intercooler, and water intercooler is actually cooling up to 40 degree Celsius. So cooling within the water intercooler is done up to 40 degree Celsius. Is this one clear? So 1 to 2 I will be having this process inside the compressor, because it is given that exit state is saturated state. Okay. Then 2 to 3 I will be having intercooling. Then 3 to 4 I will be having flash intercooling. Okay. And moreover, at point 4 I will also get some vapor from this flashing process and some vapor from evaporator 2. Evaporator 2 also there will be some vapor. So this will be process 4 to 5. And then I will be having 5 to 6. After 6, what I will be having? Seven, okay, and then 6 to 8, subcooling is also there, okay, and then 8 to 9. Now whenever we have to do this problem, already we have the enthalpy data, okay. So now from your previous problem, can you tell me what are the enthalpies known to us? We know H1, how much is H1? Please quickly tell me. 15. I have S1 equal to 6.174. 714. Which will be S2. Then I know S2 and PE2, because evaporator 2 is operating at minus 2 degree Celsius. Corresponding to minus 2 I know saturation pressure, so same enthalpy I will be having. H2 is how much? 1785 kilojoule per kg. H3 also I will be knowing, because I know temperature of point 3, which is 40 degrees Celsius, because 2 to 3 water subcooler is doing subcooling. Okay. So how much will be H3? 1706 kilojoule per kg. Then H4 will be nothing but saturated vapor state at minus 2 degree Celsius. So how much it is? 1602. Then I will also be having the value of S4, which is 6.12 kilojoule per kg Kelvin, and it must be equal to S5. If I know S5 and P condenser, I can calculate H5. How much is H5? 1802.57 kilojoule per kg. Okay. Then what about H6? Saturated liquid state at condenser pressure or condenser temperature of 40 degrees Celsius. How much is enthalpy? 533.7 kilojoule per kg. it will be equal to H7. Okay. Now what will be H8? H8 will be saturated enthalpy at, sorry, not saturated. H8 will be subcooled state.
Approximately saturated.
Oh, that approximation you have taken?
Yes.
So
there is no subcooled table in this.
okay, subcooled table was not there. Okay, so maybe if we give you the value for specific heat of the liquid refrigerant, then you can apply H6 minus H8 is equal to Cp times T6 minus T8. I know Cp, I know T6, I know T8. From there I can calculate the value of clear. So first point is either you need to refer to subcooled property table. If subcooled property table is not given, then second point is what we can do, we can if specific heat of the liquid refrigerant is given at the condenser pressure, then we can utilize that specific heat data, because this 6 to 8 process is happening at constant pressure condition. So I can write that H6 minus H8 is equal to Cp into T6 minus T8. If Cp is given, T8, T6 are known to me. I know about H8, I can calculate. Sorry, I know H6. I know H6, I can calculate H8. This is how you can calculate. Maybe in the given question, because we are saying that I do not have the data for Cp over here. So being in the subcooled state at present, you then take this data closer to your H6 only. Okay, so I am writing H8 is approximately close to H6. Why? Because we are having absence of two things. One is absence of subcooled property table, and second is absence of pressure. So maybe in your property table it is not there, but whenever the question will come in the exam, some criteria will be given to you. If there is no criteria given, then you make this approximation that in the subcooled state, change of enthalpy will be small, and as data is not given, so you can assume H8 equal to H6. Clear? And we know that H8 has to be equal to H9. You have got all the enthalpies? Now, you tell me, what will be m dot Lp? Very simple. M dot Lp, mass flowing through low stage compressor. Whatever is the mass flowing through the lower temperature evaporator, same will be the mass flowing through the low pressure compressor. All are clear with this point? So m dot Lp will be nothing but 10 tons of refrigeration into 3.51 divided by H1 minus H9. How much it is? How much you are getting it? Now the issue is, I do have the value for H8 and 9, but these enthalpies are from different table. So as these are from different table, it is not matching to your table. 0.0 0.029. Have you got the reason why your answer is different? Because this H9 I have considered up to this only. Okay. What I did? I made H6 equal to H8 equal to H9. Okay, so I have come to this point. So this denominator value has actually decreased. That's why your numerator is, your final answer is 0.036. But in actual practice, why I am not able to give you the enthalpy data? Because all the enthalpy I have written over here are from your table where reference state is different. My enthalpy values are significantly different from your values. But what we can do, let's do the post correction. How we can do post correction? Let us assume that answer is 0.029 and calculate H9 now. Please calculate H9 and quickly tell me. Then I need not to take this approximation. Zero 0.02977 you can take to be more precise. Please quickly tell me. Don't take much time. Let's remove this approximation. My H8 will be how much? 330.16, which is equal to H9. Okay. So it means either from the value of Cp or from subcooled table you will be calculating H8 to be 338. And if you calculate H8 to be 338, it will be equal to H9. And if you put H1 minus H9, now your answer will be 0.0297. Correct? Okay, what I need to do now? So this is nothing but the mass flowing through evaporator 1, and same is the mass handled by the low stage compressor. Now I have one more mass, which is the mass flowing through evaporator 2. How much will be mass flowing through evaporator 2? Please tell me. This is the pH diagram. From this tell me. From 7 to 4 I have evaporator 2. Correct? 7 to 2 I have evaporator 2. So m dot E2 will be 10 into 3.51 divided by H1 minus H7. And H7 is nothing equal to H6. How much is this mass? M dot E2, please tell me. Oh, sorry, I wrote it here. H4 minus H7. H4 minus H7. One I wrote. Please tell me how much it is. 0.032 kg per second. My answer is yes, 329, because 3287. So if you round it off, it is 329. Okay. Okay. What else? Again, I need to calculate m dash also. I need to calculate m dash also, because how is this block diagram? Do you remember how is the block diagram? This is my condenser. After condenser, I have some expansion valve. Through this expansion valve, there is evaporator 2. Then I have, so through this m dot E2 mass is going. From here, m dot HP mass is coming. Then m dot HP minus m dot E2 mass is going here. Then from here I am having one float, fine, through which m dot dash mass is going. Then here I am having then evaporator 1. Okay, so this mass over here is what? M dot HP minus m dot E2 minus m dash, and this must be equal to m dash LP, because below this is nothing but mass handled by the low stage compressor. So from here I can write that m dot HP has to be equal to mass going through evaporator 2 plus mass going through low pressure compressor plus m dot dash. Anyone is having any doubt about this? Have I written it correctly? So now m dot LP I have calculated, m dot E2 I have calculated. What is left? M dash. How to calculate m dash? For calculating m dash, I have to draw the other part also. So from here, m dot LP mass will come, and it is coming after the subcooler. So state 3. then it will be entering into intercooler, and from here it will be coming out as a state 4. Okay, and what state 4 will include? State 4 will include this m dash mass plus m dot LP, because m dot LP is also coming from it. Okay, so if I apply now the energy balance across this chamber, what I will be getting? Please tell me. From here m dash mass is coming with enthalpy. What is the state over here? 6. So m dash mass is coming with enthalpy H6, and then this m dash mass is all okay. Other what is coming? This m dot LP is coming with enthalpy again H6. M dot LP is again coming from here with enthalpy H3. Now this m dot is going out over here at state 8. So minus m dot LP into H8. Okay, and then minus of from the top this m dot LP and this m dash. These jointly is going with state 4. So m dot dash plus m dot LP is going with state 4 equal to 0. So this is the net energy balance under steady state. If you do this energy balance, you will be finding from here that m dot dash is equal to m dot LP into H3 minus H4 plus H6 minus H8 divided by H4 minus H6. And if you calculate from here m dash, it comes out to be 0.0075427 kg per second. Is this point clear? All are clear with this? Now you know m dash also. So can you calculate m dot HP? Can you calculate m dot HP? Tell me, can you calculate or not? What is m dot HP? M dot HP, final answer is, yes, correct, 0.0701. Okay, now can you tell me what will be work done? Work done through low stage compressor and work done through high stage compressor. M dot LP, M dot HP into H2 minus H1, and there it will be H5 minus H4. What are the values? 6.973, same. Kilowatt, and second is 13.91 kilowatt. Now can you calculate COP? What will be COP? Please tell me. $20 ton. Total refrigeration effect is 10 ton in the evaporator 1, 10 ton in the other evaporator. 10 plus 10, 20 into 3.51 divided by work will be 6.973 plus 13.91. How much it is? 3.3681. Okay. So this is how we can calculate CO. Heat rejection you can easily calculate. It will be m dot HP into H5 minus H6. Heat rejection in the condenser. Okay. Okay, let me give you one more problem statement. After that we will have quiz. So next problem is on cascade system. Okay, so whatever concepts we studied in last 4-5 lectures, we discussed the problem related to all the concepts jointly. So now last left is cascade system. So in terms of cascade system, let me read the problem statement and write down the key parameters. A cascade refrigeration system uses R13 on the LT side. So it means in low temperature cycle LT we have R13 as the refrigerant and ammonia on the HT side. Okay, and then we have the evaporator and condenser temperature are minus 75 and 40 degree respectively. So evaporator is minus 75 and condenser is 40 degrees Celsius. Fine. Now the question is, in the cascade condenser, do you know what is cascade condenser? The intermediate heat exchanger which acts as condenser for the LT cycle, evaporator for the HT cycle. So now details are about this. The cascade condenser R13 condenses at minus 20 degree Celsius. So it means the condenser temperature of LT is minus 20 degrees Celsius. What should be evaporator temperature of HT? Should it be more than this or less than this? Less than this. Then only it will be able to transfer the heat. So this is minus 25 degrees Celsius. So evaporator temperature of HT is minus 25 degree Celsius. Okay. So it means ammonia side temperature is this. Consider triple S cycle. So it means standard single stage saturation cycle on both the sides and determine the mass flow rates, work requirement and condenser heat rejection and COP of the system. This is a very simple problem. Very simple problem because it's a standard cycle. You need to draw one HT cycle, one LT cycle. LT cycle analysis is very simple. For cascade condenser, if you write down the energy balance, I have already given you. You can calculate the mass flow rate of the HT cycle. After that, from mass flow rate, you can calculate the work done for the HT cycle. Work done for LT, you have already calculated. Refrigeration effect will be only coming from the LT cycle because we are not using two evaporators here. Here our major, the load is at minus 75. So from there you can calculate COP. Let me give you the values. You can solve this problem by your own. It's a very simple problem. Two standard cycles. I'll give you the final answers. I think I do not have the answers at present, so no issue. You can solve this problem. If required, you can ask me doubts. Is this one clear? If you want me to draw the cycles, that I can draw, but it's very simple. You have to draw the standard single stage saturation cycle. So one cycle will be on ammonia plot, other cycle will be on which plot? Yes. Okay. Okay, so you can try this problem. Now we will have quiz.